Welcome to our presentation. This is our college, VKV Government Degree College, Kottapeta, Dr. B.R. Ambedkar, Konaseema District, Andhra Pradesh. In this video, I have to discuss the most important theorems on subgroups, necessary and sufficient condition for subgroup. Let us move to our presentation. This is very important theorem on subgroups. A non-empty complex H of a group G is a subgroup of G if and only if the necessary and sufficient condition A comma B belongs to H gives AB belongs to H, A belongs to H, A inverse belongs to H. Non-empty complex subgroup అవ్వాలి అంటే రెండు కండిషన్లు సాటిస్ఫై చేయాలి. దట్ ఈజ్ క్లోజర్ అండ్ ఇన్వర్స్. A comma B belongs to H, AB belongs to H is closure property. A belongs to H gives A inverse belongs to H is inverse property. The two conditions enough for a subgroup. Proof. Let G be a group and H is subset of G. Any subset of G is called a complex. H is subset of G. Part 1. Suppose H be a subgroup of a group G. This is a necessary condition. H is a subgroup of G. We prove that the following conditions. A comma B belongs to H, AB belongs to H, A belongs to H, A inverse belongs to H. Since H is a subgroup of G, by definition, H is itself a group with respect to same operation of G. Since G is a group with respect to multiplication, H is also a group with respect to multiplication. By closure property, A comma B belongs to H gives AB belongs to H. By inverse property, A belongs to H, A inverse belongs to H. B belongs to H, B inverse belongs to H. That is every element in H having multiplicative inverse. So condition 1 and 2 verified. Part 2. Suppose that A comma B belongs to H, AB belongs to H, and A belongs to H, A inverse belongs to H. This is the sufficient condition. Now we prove that H is a subgroup of G. H subgroup means it is enough to prove that H is a group with respect to multiplication. And that means H satisfies four conditions: closure, associative, identity, and inverse adjoints. The first one is closure. Now we have to prove that H is a subgroup of G. Closure property. Using condition 1, A comma B belongs to H gives AB belongs to H. AB means A dot B belongs to H. AB is A dot B. Gives dot is a binary operation in H. Second one, associative. Let ABC belongs to H. Take three elements in H. ABC belongs to H gives ABC belongs to G since H is a complex. Complex means a subset. H is a subset of G. By definition of subset, all the elements in H are the elements in G. So ABC belongs to H gives ABC belongs to G. Since G is a group, given condition, G is a group, satisfies associative. That is A dot B dot C is equal to A dot B dot C. That gives dot is associative in H. All the elements in H are the elements in G, where G is a group satisfying associative property. Next, identity adjoint. By using condition 2, A comma B belongs to H gives A inverse comma B inverse belongs to H. Therefore, A belongs to H, A inverse belongs to H gives A inverse belongs to H using 1. Using 1 means A comma B belongs to H gives AB belongs to H. So here A belongs to H, A inverse belongs to H, A inverse belongs to H. Since A inverse belongs to H and H is a subgroup subset of G, all the elements in H are the elements of G. That gives A inverse belongs to G. Since G is a group, by inverse property, A inverse equal to A inverse A equal to E, where E is the identity. So that is A inverse is E, that is E belongs to H. For any A belongs to H, A belongs to G, since H is subset of G, A belongs to G and AE is equal to EA is equal to A, that gives E is the identity element exists in H. Inverse adjoint. Let A belongs to H gives A inverse belongs to H using 2. Therefore, A belongs to H, A inverse belongs to H, gives A inverse belongs to H using 1. That is, A comma B belongs to H gives AB belongs to H. Here A inverse belongs to H. Since H is subset of G, H is a complex given condition. All the elements in H are the elements in G. That is, A inverse belongs to G. Since G is a group, G satisfies 4 conditions: closure, associative, identity and inverse. By inverse property, A inverse equal to A inverse A equal to E, where E is the identity. Therefore, A belongs to H gives A inverse belongs to H, and A inverse equal to A inverse equal to E. Clearly, all the elements in H having multiplicative inverse. Therefore, H satisfies all conditions: closure, associative, identity and inverse, and H is subset of G. Clearly, H is a subgroup of G. This is the very important theorem, necessary and sufficient condition for a subgroup. H is a subgroup of G if and only if it satisfies 2 conditions: closure and inverse. 2 conditions enough for a subgroup. Hence proved. One more important theorem. Prove that a non-empty subset H of a group G is a subgroup of G if and only if A comma B belongs to H gives AB inverse belongs to H. Non-empty subset H గ్రూప్కి ఉండేటువంటి నాన్ ఎంప్టీ సబ్గ్రూప్ అవ్వాలి అంటే ఒక కండిషన్ సాటిస్ఫై చేయాలి. దిస్ ఈజ్ ది నెసెసరీ అండ్ సఫిషియంట్ కండిషన్ ఫర్ ఏ సబ్గ్రూప్. ఇంతకుముందు థియరంలో మనం సబ్గ్రూప్ అవ్వాలి అంటే 2 కండిషన్స్ చెక్ చేసాం. 2 కండిషన్స్ ఏంటవి? క్లోజర్ అండ్ ఇన్వర్స్ ప్రాపర్టీ. ఆ 2 క్లబ్ చేసి ఒకే కండిషన్లో ఏబీ ఇన్వర్స్ బిలాంగ్స్ టు హెచ్. ఏబీ ఇన్వర్స్ మీన్స్ ఏబీ ఇన్వర్స్ A dot B inverse. A dot B means is closure and B inverse. So inverse and closure రెండు క్లబ్ చేసి చేసినటువంటి థియరం. వెరీ ఇంపార్టెంట్ థియరం. నెసెసరీ అండ్ సఫిషియంట్ కండిషన్ ఫర్ ఏ సబ్ గ్రూప్. ప్రూఫ్. లెట్ G be a group and H is subset of G and E is the identity element in G. Part 1. Suppose H be a subgroup of G. We prove that A comma B belongs to H gives AB inverse belongs to H. This is a necessary condition. Since H is a subgroup of G, by definition, H is itself a group with respect to same operation of G. Since G is a group with respect to multiplication, H is also a group with respect to multiplication. Let A comma B belongs to H. A belongs to H. Since H is a group satisfying all conditions: closure, associative, identity and inverse. By inverse property, A belongs to H gives A inverse belongs to H, and B belongs to H gives B inverse belongs to H. Therefore, A belongs to H and B inverse belongs to H gives AB inverse belongs to H. This is closure property. Since H is a group, we are using 2 conditions: inverse and closure axioms. Therefore, A comma B belongs to H gives AB inverse belongs to H. The necessary condition is verified. Second part 2. Sufficient condition. Suppose A comma B belongs to H gives AB inverse belongs to H. We prove that H is a subgroup of G. It is enough to prove that H is a group. H is a group means H satisfies 4 conditions: closure, associative, identity and inverse. Next, first one is identity axiom. వెరీ ఇంపార్టెంట్ కండిషన్. గ్రూప్ అనగానే మనకు 4 కండిషన్లు సాటిస్ఫై చేయాలి. ఆ 4 కండిషన్లో ఫస్ట్ క్లోజరు, అసోసియేటివ్, ఐడెంటిటీ, ఇన్వర్స్ ఉండాలి అనేటువంటి రూల్ ఏం లేదు. అక్కడ మనకు ఉండే 4 కండిషన్లు ఏదో ఒక కండిషన్ ఫెయిల్ అయింది అనుకోండి, ఎనీ వన్ కండిషన్ ఫెయిల్, దెన్ ఇట్ ఇస్ నాట్ ఏ గ్రూప్. సో అందువల్ల మీరు గ్రూప్లో ఫస్ట్ మనం ఐడెంటిటీ చెక్ చేయొచ్చు, లేదా ఇన్వర్స్ చెక్ చేయొచ్చు, అసోసియేటివ్ ఏ కండిషన్ అయినా చెక్ చేయొచ్చు. మనం 4 కండిషన్లు చెక్ చేయాలి. సో మనకి ఫస్ట్ ఐడెంటిటీతో స్టార్ట్ చేద్దాం. ఫస్ట్ వన్ ఈజ్ ఐడెంటిటీ axiom. Let A belongs to H. Take one element. A belongs to H. By using 1, A comma B belongs to H gives AB inverse belongs to H. Take B is equal to A in 1. A comma A belongs to H gives A inverse belongs to H. Using 1. A inverse belongs. Since A inverse belongs to H gives A inverse belongs to G, since H is a subset of G, all the elements in H are the elements in G. So A inverse belongs to G, where G is a group, G satisfies 4 conditions. By inverse property, A inverse equal to A inverse equal to E, that is A inverse belongs to H gives E belongs to H. E belongs to H. For any A belongs to H, all the elements in H are the elements in G, since H is a subset of G. So A belongs to G, where G is a group and AE is equal to EA is equal to A, where E is the identity element. Hence, the identity element E exists in H and AE is equal to EA is equal to A. Identity axiom verified. Next, the second one, inverse axiom. Let A belongs to H and E belongs to H. Already E exists in H identity element. Using 1, A comma B belongs to H gives AB inverse belongs to H. Here E comma A belongs to H gives EA inverse belongs to H. Using 1. EA inverse, E is the identity element. So EA inverse is A inverse E is equal to A inverse, that is A inverse belongs to H. A inverse belongs to H, therefore A belongs to H, A inverse belongs to H, that gives all the elements in H having multiplicative inverse. Next, third one is associative. Take 3 elements in H. A comma B comma C belongs to H gives ABC belongs to G. Since H is subset of G, all the elements in H are the elements in G. ABC belongs to H means ABC belongs to G. That is, G is a group satisfying associative property. So A dot B dot C is equal to A dot B dot C. That is, dot is associative in H. Next, closure axiom. Take 2 elements. Let A comma B belongs to H. Gives A inverse comma B inverse. A belongs to H, A inverse belongs to H. B belongs to H, B inverse belongs to H. Already inverse exists. For A belongs to H, B inverse belongs to H gives A B inverse whole inverse belongs to H. Using 1, A comma B belongs to H, A B inverse belongs to H. So B is replaced by B inverse. So here B inverse, take B inverse. A comma B inverse belongs to H gives B inverse whole inverse. This is A B inverse whole inverse belongs to H. A inverse, since A inverse whole inverse equal to A, that is B inverse whole inverse is B. So AB belongs to H. AB means A dot B. So A dot B is dot is a binary operation in H. Clearly, H satisfies 4 conditions: closure, associative, identity and inverse. Therefore, H is a group and H is subset of G given condition. H is subset of G, H is a group, because H is a subgroup of G. It's a very, very important theorem. H subgroup if and only if A comma B belongs to H gives AB inverse belongs to H, hence proved. One more important theorem. Prove that a finite non-empty complex H of a group G is a subgroup of G if and only if A comma B belongs to H gives AB belongs to H. Only one condition, closure property, is enough for a subgroup if H is finite. Very, very important. H is a finite non-empty complex. Non-empty complex means a subset, non-empty subset. Already we have proved H is a subgroup of G if and only if 2 conditions. A comma B belongs to H gives AB belongs to H, closure property. A belongs to H gives A inverse belongs to H, inverse property. 2 conditions, closure and inverse, if and only if H is a subgroup. Here H is finite, only one condition is enough. Very, very important theorem. Proof: let H be a finite non-empty complex of a group G, non-empty subset of a group G. Part 1. Part 1 is necessary condition. Suppose H be a subgroup of G. H be a subgroup of G, we have to prove that A comma B belongs to H gives AB belongs to H. Since H is a subgroup of G, by definition, H is itself a group with respect to same operations of G. Since G is a group with respect to multiplication, then H is also a group with respect to multiplication. Since H is a group, H satisfies four conditions: closure, associative, identity, and inverse. By closure axiom, A comma B belongs to H gives AB belongs to H. So necessary condition is verified. The part 2, this is sufficient condition. Suppose A comma B belongs to H gives AB belongs to H. It is denoted by equation 1. Now we prove that H is a subgroup of G. H is a subgroup of G means H satisfies two conditions. A comma B belongs to H gives AB belongs to H is a closure property. A belongs to H, A inverse belongs to H. This is inverse property. The two conditions enough for a subgroup. Already we have proved the very important theorem. H is a subgroup of G if and only if it satisfies two conditions. It is enough to prove that inverse element exists. Every element in H having multiplicative inverse. Already closure condition exists. A comma B belongs to H, AB belongs to H. Equation 1. Inverse axiom. Let A belongs to H. A belongs to H. Replace B by A in 1. A comma A belongs to H gives A into A belongs to H. That is, A belongs to H, A belongs to H, A into A belongs to H. A into A is A square. A square belongs to H. Again, A belongs to H, A square belongs to H. A into A square also belongs to H. A into A square is A cube belongs to H. This is A belongs to H, A cube belongs to H, gives A into A cube also belongs to H. This is A power 4 belongs to H. Similarly, we get A power 5 belongs to H, A power 6 belongs to H, and so on. A power m belongs to H, and so on. Similarly, we are continuing in this way. We get a set H is equal to A square, A cube, and so on, A power m. These are all infinite in numbers. Since H is a finite set, given condition, H is, then there must be some repetitions exist in the elements of H. That is A square, A cube, and so on, A power m, and so on. Suppose two elements equal. A power m is equal to A power n for any m comma n belongs to n and n greater than m. It is denoted by equation 2. Two elements equal. A power m is equal to A power n. Both sides multiply with A power minus m. A power m into A power minus m equal to A power n into A power minus m. So A power m minus m, since A power m into A power n equal to A power m plus n. Here minus A plus of A power m plus of minus m, m minus m, equal to A power n minus m. A power m minus m is A power 0 equal to A power n minus m. A power 0 is E, very important. A power 0 is E. Since A power m belongs to H, A square, A cube, and so on, A power m belongs to H. Since H is subset of G, all the elements in H are the elements in G. Since A power m belongs to H, A power m belongs to G. Since G is a group, G satisfies inverse condition. So A power, every element in G having multiplicative inverse. So A power m inverse also belongs to G. A power m inverse is A power minus m. Since A power m whole power n, this is equal to A power mn. So A power minus m belongs to G. So A power m belongs to G, A power minus m belongs to G, inverse elements. We know that A inverse equal to A inverse A equal to E. Now A into A power n minus m minus 1 is equal to A power 1 plus n minus m minus 1. Since A power m into A power n, this is A power m plus n. So 1 cancel, that is A power n minus m. Using 3, A power n minus m is equal to E. That is A power n minus m is E. Again, A power n minus m minus 1 into A. That is equal to A power n minus m minus 1 plus 1. And 1 cancel. This is A power n minus m is E. Therefore, A into A power n minus m minus 1, that is equal to A power n minus m minus 1 into A is equal to E. We know that A dot B is equal to B dot A is equal to E gives B is equal to A inverse. That is the inverse property. So here A power n minus m minus 1 is equal to A inverse. So A inverse. So A belongs to H, A inverse is also belongs to H. A power n minus m minus 1 is the inverse element of A. That means every element in H having multiplicative inverse. Satisfying closure and inverse, then we say that H is a subgroup of G. This concludes that H is a subgroup of G. Here observe, H is a subgroup of G if and only if it satisfies two conditions, closure and inverse. Hence proved.